That talk is a general comment on the fact that we as functional programmers import a lot of structures from the world of abstract mathematics and category theory in particular. But we need to remember that we import not only structures themselves that we implement in our programs, we also import reasoning principles. And so there are two things that we want our reasoning principles to be. And so we want our reasoning principles to be equational, so that we can reason by chains of equalities between programs. And we want them to be expressive. That is, by that I mean that they need to preserve some higher level, higher order properties of the structures from this abstract nonsense world. And the purpose of this talk is to show you some properties like that would allow us to reason about free monads more easily. So the free monad is kind of a generalized term monad where the signature is given by an arbitrary functor, and the monadic structure is given by substitution in the variables. And we know the usual Haskell data type to encode free monads, and for the purpose of this talk, it is good to think about free monads as kind of terms in a deeply embedded language, where the endo functor is the signature, that is the set of operations that we use to build programs that we encode as free monads. And because a free monad is kind of a composition of many Fs, so we will also use the notation F star. So it's kind of like a cleany star, right? So the problem is that as we just saw, free monads are given by inductive data types, and inductive data types come along with a reasoning principle, which is called structural induction. But there is a small problem with structural induction, that it knows only about the shape of the algebraic data type, but it knows nothing about the underlying monad structure of the free monad. And we would like to be able to prove properties easily that preserve the monadic structure, that are somehow coherent with the monadic structure of the free monad. So as an example, consider there's in the Haskell libraries you can find something called free monad transformer, which is a monad M composed with the free monad generated by composition of F and M. So, and then imagine that someone asks you to prove the monad laws that this free monad transform is indeed a monad. And that would mean that if you wanted to prove like associativity of join, you have like 3 layers of this, and you have 2 nested structural inductions. And I think the proof could give you a headache. And I know because I once proved something similar. So this is like a screenshot of a paper I had with Jeremy once, where I prove kind of a monad loss of a similar monad, not the same one, but the proof is long, the principle is the same. So this can give you a headache, even a greater one than the one from drinking sake. My goal is to show you that we can first find the principles that will make such proofs much easier. And one of the tools I want to use to make things simpler is like a framework of string diagrams. So a quick guide to string diagrams. So a string diagram is a 2-dimensional notation that we use to denote expressions. And they are useful for presentation of more complicated expressions, especially ones that involve a lot of composed functors, right? And the nice feature of string diagrams is that they have some administrative equalities built in. That means that whenever 2 expressions are equal by such an equality, we don't have to put that equation in the proof, because the 2 things have the same representation as a string diagram, right? So I think an example will give you a good overview of what's going on. So first consider a function lookup. It's a function that involves a lot of functors. So lookup k looks for an item under the key k in an association list. So the type of lookup k so it's a function that is polymorphic in A, so more precisely like a natural transformation. It's natural in A. And like an input of this function is like the composition of the function of the functors list and key paired with something, and the applied to A, and the output type is the maybe functor applied to A. So we can also use some more compact mathematical notation. Just ignore this A. We will work with what people sometimes call natural transformations. And we can draw such a natural transformation using a string diagram like this. So a natural transformation is like a dot, a node, and the node has a number of incoming edges, incoming strings, and a number of outgoing strings, and they represent functors, like the composition of functors if you go from left to right. And in this case, lookup K is natural transformation from list composed with key paired with something. So we have two incoming strings, and the result functor is maybe. So we have one outgoing string called maybe. Okay, so what happens if we have two functions written as string diagrams? So we also have concat, which concatenates a list of lists into one list. So we have two incoming edges and one outgoing edge, right? So you can see if an outgoing edge is of the same type as an incoming edge of another diagram, then it is quite tempting to compose them together like this, right? And so this is a string diagram. That is simply a different notation for a function lookup K after concat, right? So the fact that concat is polymorphic means that we don't care what is on this side of this string. So it could be key paired with something or any other functor or maybe nothing, right? So another example. If we want first, for example, to reverse the inner lists, right? So we want to encode a function like lookup K after concat after fmap reverse. So fmap means that we don't touch the first endo functor, the first layer, but we reverse what's inside. So fmap like puts the reverse on the right string. That is, we reverse the inner lists. Okay. So this is what we need to know about string diagrams for this talk. So now we can safely go back to free monads, right? So one thing we can note about free monads is that we know this data type, but there are other possible implementations of free monads, like the one by like a codensity monad or something. So maybe it's not that free monad is a thing. Maybe being free is a property of a monad, right? So if it's a property, then maybe it should have an interface, something like a type class, that a monad is a free monad. Should be M, probably somewhere there. So, but if it's a property and we would like to come up with a interface to work with free monads, the question is what are the operations and laws that characterize free monads, right? So the simplest ones come from the fact that free monads is like free monad is free in the mathematical sense. There is a definition what three free things in mathematics are. So let's just entangle this definition and let's see what happens. The mathematical definition says that there are two important operations related to free monads, and one is called emb, like embedding. And intuitively, it says that we can go from like a single operation to a free monad. That means we have a single operation, and you can treat it as like a one operation term, right? So we embed and we create one layer term with one operation, right? So this is kind of a constructor of the free monad. So how about a destructor? So if we have a term, we understand it as a syntax of a language. So what do we do with syntax? We interpret syntax. So we have this function interp, and what do we need to interpret a language? So we need first some domain in which we interpret the syntax, and a domain is given by a monad. So for example, like an I/O monad, right? We have a program and we want to execute it. So we interpret in I/O by interpreting print as an operation into print ln in Haskell. And what we need to provide is like interpretation of operations. So if you know how to interpret each operation, we can like spread it across the whole structure, interpreting the whole term, the whole program. So this is what interp does. So we introduce this notation with floor brackets, and in the string diagrams, we denote it using a box. So notice the types, that the incoming edge of this function f that interprets operations is just f. So we interpret single operations. And there is like a small hole right here to stress that the type of the string that comes out from f is the same as the string that comes out of the box, right? So it's important that this thing is a monad morphism. Never mind what monad morphisms are. We just need to remember that this is a monad morphism, right? And I forgot to say that we denote emp because it's such an important function that we have a special notation for that, and it's like a blue triangle pointing down. All right, so what are the laws that need to be satisfied? So if someone's interested in recursion schemes, they will surely recognize at least the names of the laws and general shapes of the laws. So the first one is called cancellation. And intuitively, it says that if you have single operation and you wrap it and you understand it as like embed into the monads, we understand it as a single operation term, and then we interpret that term. It is the same as if we didn't bother to wrap it and just interpret that operation. So in symbols, it just says interp f after emp is f. And the intuition for the diagrams is that whenever the blue triangle goes down and hits the box, they both disappear, right? Another law says that because the free monad is also a monad, so we can imagine that the free monad is like our domain of interpretation. So we can interpret syntax in the free monad. So we take an operation and we say, oh, so the interpretation of my operation is syntax. It's just this operation. We wrap it. And obviously, this won't do much good. Like this nothing changes. So if we interpret using this embedding thing, we get identity, right? So there are no nodes on this string because it's just an identity, right? And the third law, which was fusion, which is like a more complicated one, says that whenever we interpret something in one domain and then we transfer that into another domain, so because monads are our domains, we use monad morphisms to translate between them, then we can first interpret the whole term and then translate it into like a new domain, or we can translate every time we interpret an operation. And the fusion law says that it is the same thing. And in string diagrams, it just means that a monad morphism, but not any morphism, it needs to be a monad morphism, can like slide in and out of the box. It uses this hole to do that. All right, so example is in order. So one interesting operation on free monads is kind of renaming. If we have two functors and a function between them, natural transformation, then we can kind of rename the nodes, the operations using these functions. And this, I believe in Haskell libraries, this operation is called hoist, right? So the definition is very simple. We just for every operation, we first rename this operation to this new signature G, and then we say that, oh, so G is just a syntax, so we embed it, right? And one question we can ask is what happens if we have three functors and two such translations? So there are two ways we can put everything together. One way is to first rename the term using the first renamer, the first translation, and then rename the result using the second translation, or we can just compose these two renamers and then use that to rename the whole term. The question is whether these two things are equal. So the one on the right seems a bit more efficient, at least intuitively. So we would like this law to hold. So let's prove that it really holds. So we start with the left-hand side. And we remember that the red box, I mean it's yellow box. The yellow box is a monad morphism. And we know that monad morphisms can slide up and down, and then they can go into the box. Right? It's called fusion. So let's just apply fusion. And as we remember, what happens when the blue triangle hits the box? So they both disappear. That law is cancellation. And ta-da, the proof is done. It wasn't very difficult, right? There is a small problem with this. It's all fine and easy. But going back to our example of the free monad transformer, what we know about free monads at the moment is not enough to define or prove that the free monad transformer is indeed a monad. But there are other interesting properties that hold for free monads, because like the category of Haskell types is rich enough. So one has to do with something that Dominic was talking about, that is distributive stuff. Like we have, imagine we have this thing, which is kind of distributes functor f over g. It is like has two incoming edges, two outgoing edges, and we can find such functions like the sequence function, or there's this traversable class. Like that's all about distributing one thing over the other thing, right? So this property turns out, this kind of distributivity seems to be very important in the theory of monads. So, it turns out that free monads in Haskell are distributable in the following sense: that given such a function, we can lift the distribution of f over g to a distribution of the free monads generated by f over g. So here we can like swap these two things, and here, because f is kind of like an f composed with itself many times, we can simply like distribute layer by layer, right? And this operation of lifting this function to this distributivity of the whole monad will be denoted by this green honeycomb cell, right? And this also has some interesting properties. We will not go into details, but let's just look at some pictures. So there's cancellation again. So if we have only one layer, then obviously distributing this over the whole structure, which is a one-layer structure, is the same thing as just using F1s, because we have only one layer. So again, when the blue triangle hits something, this thing disappears. There is reflection, which says, so there is nothing here, so we should interpret this as an identity functor, nothing here, so we should understand this as identity natural transformation. So if nothing happens, then nothing happens. And there is fusion is a bit more complicated, although it is pretty intuitive. So we can either first distribute j, I mean f star over j, and then k over the result, or we can just distribute them together in kind of a lockstep, that we just distribute j, distribute k, and so on, and that gives the same result, right? So the same laws. There is one important law which seems pretty awfully complicated, but the point is that if there is a function on the outside and a function on the inside, then we can kind of shift this thing up and down. So this is the law we actually discovered in the paper. And it seems not to follow from the cancellation fusion reflection laws, but it pops out in almost every proof that we do about distributivity of free monads. All right, so there are some laws, never mind the details. So remember this proof, and using these properties and one or two additional lemma, this proof looks more or less like this, right? So it boils down to four equalities plus like an additional lemma. There's some notational stuff going on here, but never mind the details of this proof, but just number four equalities, right? So there's more in the paper because the cool stuff actually begins where I end. And so I invite you to read the paper and get on the track and bring us some more fun stuff from the world of mathematics. Thank you.
So, do we have any questions? There's one here.
Hi, Mark Hopkins, Combank. So, in the paper, you say that you mentioned and there's different categories of free monads, so the foldable and so on, that in some cases, like a co-Cartesian closed category, and also in Haskell, these just reduce to free monads. Mm-hmm. Are there interesting cases where these are actually new notions?
Nope. So I can come up with a category where the free monad is not given by the initial algebra. But to be honest, I don't know of any examples that a free monad given by. So I don't know of any examples of a free monad that doesn't have this property, right? So in general, if you just accept the definition that free monad is given by emp and this interp stuff, there is nothing that, I believe, there is nothing that forces this property to happen, right? But in categories rich in structure, like Cartesian closed categories where with co-products, where every free monad is given as an initial algebra, then this green property always holds. So if we are like in the rich categories, then we know that these properties hold. And when they're not, then the categories are probably not that interesting for like doing functional programming in them.
And just a small note about terminology. You talk about two categorical reasoning. So I think usually that's reserved for when you're in a three category and you're talking about two morphisms. So I think this is just like categorical reasoning.
So, all right. So string diagrams in general are good notion for doing reasoning in two categories, right? Strict two categories where they are somehow complete with respect to the axioms of a two category. So this is the reason why I say that this is more like a two categorical reasoning, because string diagrams come from that area, right? So this is more like string diagrams in a monoidal category, right? Because we have only one category, we have only endo functors, we don't have functors between different categories.
Okay, maybe we can talk about it after.
Okay.
One last question, right at the back.
Chaz Leichner, X. I don't see any reason that I'd be any better at doing this correctly than writing out equations correctly. Are there any proof assistants that I can draw these pictures in?
So there are some proof assistants that you can find that use string diagrams. So they're much more advanced than this, because they are mostly used by physicists to do their crazy four-category theory. And I played once with one called Globular. I tried to prove something simple, but the interface is not that good yet. So it's hard to use, but there are some theorem provers for string diagrams, and you can find them online and use in your browser.
Great, thank you very much.
Okay.
Oh, so
Thank
let's
you.
thank Maciej again.
Microphone.